recording. And I'm going to go ahead and share my screen as well. Sorry. Screen share. Include sound. Yep. Okay. So, okay. First of all, I hope you guys are all okay. These days, the pandemic is getting worse and worse. So be careful with COVID-19. Try to not try not to get exposed to the virus. So stay away from crowds. I have, some relatives who got infected. So these days are difficult. Be very careful. Last time we were left with the electric motor, I kind of tried to explain, how electric motors work using this video. I don't know if you have any questions about that, but these kind of practical things are important. After you graduate as an engineer, when people ask you about how the basic electric motors work, etc. These are important stuff. Please be aware of those things. So let me go ahead and start from where we left. Okay, so we always talk about electrons and holes. The concept of hole is quite new to you. Electrons, you always knew them. Electrons are particles that are negatively charged. They're, not imaginary particles. They are real particles. But holes, for example, we said they are basically the absence of electrons. So we talked about semiconductors. We said that, some of the so for example, for silicon, we said, there is a valence state and conducting state, and you lose some electrons. You donate some the silicon donates some electrons to as external atomic species, and the valence state becomes electron deficient, and we call that electron deficiency holes. Holes behave like positively charged particles. And some materials conduct with electrons, some conductors conduct with holes. Typically, materials conducting with holes are semiconductors. Some semiconductors can have metallic conductivity. They can be quite good conductors. That's what I mean. So, how do you know if a material is conducting with electrons or holes? There is a very simple experiment, but very beautiful, elegant experiment, which can reveal if a material is conducting with holes or electrons. So here's what you do. The experiment is called Hall effect measurement. So what you do is you get a piece of, a plate-like rectangular piece of a material, and you push of a conductor, and you push current through it. Jx is the current here, and you also apply a magnetic field perpendicular to the plate, and you measure voltage drop across the edges, the long edges of the conductor plate. So here's what happens. If the material is conducting with electrons, let's say, the electrons, go in the opposite direction of the current, as you may remember. So current flows in the positive x direction, and electrons then should be flowing towards the negative x direction if the material is conducting with electrons. So when you try to find the direction of the force on the electrons due to the magnetic fields, since electrons are moving in magnetic field, they should be experiencing force. So use your right hand rule. Your middle finger should be pointing the direction of By, the magnetic field direction, which is, I think, is positive Y direction in this scenario. And the electrons are moving in the negative X direction. Well, anyways, then the force, the magnetic force, the magnetic force for a positive particle would be in negative Z direction, but since it is an electron, the force is Fz here. It is in positive Z direction. Okay. And what happens is, now the electrons, as they are moving, they travel like this. They make a path like this, not a straight path, between along the x-axis, but they just get deviated from their path, and this part, the bottom part of the plate becomes positively charged locally, and the upper part becomes negatively charged. So when you measure the voltage across point A and B, when you measure VAB, you get a positive value, positive voltage, positive hole voltage. Okay, this is what you see with the electrons. For electrons. And for positive charge particle, you push the current in the same manner, in the same direction. Okay, positive X direction. The magnetic field is in the same direction with the previous example. So basically, you apply the same conditions externally. And what happens is, for the positive charge particle, since for the positive charge particle, the current direction and the movement of the particles, for example, holes, are in the same direction, you apply the, right-hand rule this time. The magnetic field is in the shown direction, but this time drift velocity is not towards minus x, is towards positive x direction. So the force again in positive z direction. This time holes make a movement like this. Their path gets deviated and they move like this. However, this time the upper part of the plate is positive charged. The bottom part is negatively charged. And when you measure the voltage between VAB, you get a negative voltage, negative hole voltage. Okay, this is for holes. Okay, this is how you know if the particles, charge carrying particles in a conductor is electron or are electrons or holes. If the voltage drop here, for example, between VAB is positive, then you know that conductor is conducting with electrons. If the voltage drop between A and B is negative, then you know that it's conducting with holes. Okay, this is a very important information, especially for electronics engineers and material scientists. Okay, let me erase this stuff and let me explain the math beyond that. So we have, after we apply the magnetic field, travel in a deformed path here, an electric field forms because of the voltage drop. For example, for this scenario, let's say electric field is in positive z direction. Q is the force, electric force, Fe, let's say, is in negative z direction, and electric force and the magnetic force Fz, they balance each other, so they should add up to 0. Okay, they should add up to 0. Okay, QEZ plus QVD should be 0. And this is VD is with velocity. As you know, QVD is the FC. This is FC. This is FE. They should add up to 0. Since they are facing opposite directions, okay, we add them like this. And this gives VD equals to minus EZ over BY. But we know that, current density is NQVD. We leave, and we say NQ is J over VD. Then combining this equation and this one here gives you NQ is equal to minus J BY over EZ. For example, for an electron, you put 1.6 minus 1.6, 1009, 10 minus 19 coulombs for Q. And for current, you put the current value you have in amps, magnetic field value with Tesla, and for electric field is going to be volt per meter. Okay. And, Tesla is ampere, Newton per ampere meter. Okay, amperes cancel out. And meters cancel out. And what you have is then Newton per volt. You have Coulomb, right? So then you have Newton per volt Coulomb. So this should be number of particles per unit volume. 2 meters cancel out each year. I think I made a mistake. Newton per ampere meter divided by, okay. Just give me a second. I need to think about it here. Yeah, this was correct. And volt should be joule per coulomb, right? Okay. Volt should be joule per coulomb. Okay, coulombs cancel out. Joules should be Newton meter. And I end up having 1 over meter. I'm making a mistake here. Oh, this is current density, not current. Okay, so this is amperes per meter square. Current density. That's why then we already had 1 over meter. We should have 1 over meter cube, and that's, yes, that's correct units for number of particles per unit volume. Let me do this again so that you don't get confused. So I'm just trying to make sense about the units. Okay, so here's the deal. The charge here is coulombs. The current density is amperes per meter square. By is the Tesla, that's the magnetic field. Tesla is also at the same time Newton per ampere meter. Okay. E field is volts per meter. Volts by definition is joules per coulomb. So what we have is number of particles, coulombs, ampere, Newton, ampere, meter, cube, joules over meter, coulomb. And we had this coulomb, we can move it to here. Okay. So coulombs cancel out, amperes cancel out, one of the meters cancel out. So number of particles is then Newton per joule meter square. Joule is Newton meters by definition. Work is, path multiplied by force, as you know. So it is going to be Newton per Newton meter cube. And you have now maybe 1 over meter cube for number of particles per unit volume. So that's how the units make sense. Arkadaşlar, Türkçe'de açıklayayım. Hep elektronlardan ve hollardan falan bahsettik. İşte dedik elektronlar negatif yüklü, hollarda işte pozitif yüklü olduğu düşünülen parçacıklardır. Daha çok elektron yokluğu holların varlığına işaret eder. Ama en nihayetinde bir elektrik devresinde hollarla ileten bir şey için bunu söyleriz ki pozitif parçacıklı yükler elektriği iletmektedir. Dolayısıyla elektriğin akım yönüyle pozitif parçacıklı yüklerin yönü aynıdır hollar ilettiğinde. Şimdi mesele şu. Diyoruz ki elektron iletiyor, hol iletiyor. Peki bunu nasıl bileceğiz? Yani bir iletkeni aldık. Üzerinden akım geçirdik. Sonuçta baktığında aynı. Elektronlar ileten de, hollar ileten de akımı aynı yönde geçiriyor. Aynı şekilde voltaj uyguluyorsun. Nereden biliyoruz yani? Elektronlar mı iletiyor? Yoksa hollar mı iletiyor elektriği? Bunun için basit bir deney var arkadaşlar. Bu deneye Hall efekt ölçüm deniyor. Bir tane plaka şeklinde dikdörtgen plaka şeklinde malzeme alıyorsunuz. Diyelim ki ilk önce ne olduğunu bilmiyorsunuz. Ona manyetik alan uyguluyorsunuz. Aynı zamanda bir akım pompalıyorsunuz malzemeye. Jx burada akım yoğunluğu. Malzeme elektronlar iletiyorsa biliyorsunuz elektronlar işte akımın ters yönde hareket ederler. Şimdi manyetik alan uygulayınca sağ el kulağına baktığınızda sağ el kulağına göre bir elektron, biliyorsunuz sağ el kulağına uyguladıktan sonra pozitif parçacık olsa mesela burada eksi z yönünde şey olacak, kuvvet olacak ama elektron olduğu için artı z yönünde bir şey olması lazım. Bir kuvvet, manyetik alan kuvveti oluşması lazım. Dolayısıyla elektronlar hareket ederken rotaları değişiyor azıcık. Rotaları böyle yukarıdan akacak şekilde değişiyor. Bu da anlık olarak plakanın üst tarafında elektronların daha fazla olmasının, alt tarafında elektronların daha az olmasına sebep oluyor. Dolayısıyla A ile B nokta arasında bir voltaj düşümü ölçüldüğünde artı bir değer ölçülüyor. Elektronlar için böyle oluyor. Pozitif parçacıklar için pozitif parçacıklar akımla aynı yönde akacağı için yani dışarıdan bakıldığında aynı şey yapıyorsunuz. Manyetik alan aynı yönde uygulanıyor. İşte akım aynı yönde pompalanıyor vesaire. Ama bu sefer artı yüklü parçacıklar olduğu için sağ kuralıyla manyetik alanın uyguladığı kuvvete baktığınızda manyetik alan dolayısıyla uygulanan kuvvete baktığınızda artı yüklü parçacıklar bu sefer plakanın üst tarafında birikecekleri için bu sefer voltajı A ile B noktasına ölçtüğünüzde bu sefer eksi bir voltajı ölçersiniz. Dolayısıyla deneyde şunu biliyorsunuz. Yani ben aynı manyetik alanı, aynı akımı uyguladığımda malzemeye eğer voltaj düşümü A ile B noktasındaki voltaj düşümü artıysa malzeme elektronlarla iletiyorlar. Normal metalik malzemedir. Ama voltaj düşümü eksi oluyorsa bu sefer diyorsunuz ki malzeme benim hollarla ileten muhtemelen bir yer iletkendir. Tamam, bu işin matematiğine girdim biraz. Daha fazla onun detayını çok fazla şey yapmayacağım. Ama gördüğünüz gibi kuvvetleri eşitleyerek bir denklem çıkarıyorsunuz. Elektrik alan oluştuğu için bu voltaj dolayı elektrik kuvvetiyle dengede olmak zorunda. Manyetik kuvvet dengede olmak zorunda. Birbirine eşitliyorsunuz. Ters yönde olduğu için böyle artı dedim. Yani dolayısıyla eksi Fi eşittir Fz demeye çalıştım burada. Buradan işte çıkardığınızda current density için olan denklemi getiriyorsunuz buraya. Çünkü V drift'i orada ortadan kaldırmaya çalışıyoruz. NQ eşittir eksi C bölü B, eksi C B'ye bölü EZ diye bir denklem çıkıyor. Bunu işte ben burada yaptım. Birimsel sağlamasını yaptım. Birimsel sağlamayı siz kendiniz her zaman yapın arkadaşlar. Size çok faydası dokunur. Birimler çünkü bu işin aslıdır. Formüllerin gerçekle bağlantısı birimlerdir. Okay, now let's do an example about Hall effect measurement. So here we have a material that's unknown. We apply voltage, between these 2 points. This is positive terminal. This is negative terminal. So we are basically pushing current in this direction. Okay. We have a magnetic field upwards in this direction, perpendicular to the plate. So now the question is, if voltage drop is larger than 0, what is the charge carrier type? I would like you guys to answer this one. Arkadaşlar bu sorunun cevabını sizden bekliyorum. İsterseniz chat odasında cevaplayın, isterseniz sesli cevaplayın. Burada bir malzememiz var. Malzemeye işte bir voltaj uyguluyoruz. Dolayısıyla bir akım geçiriyoruz malzemeden. Akım yönü işte bu şekilde. Manyetik alan yönünde işte yukarı doğru plakaya dik. Voltaj A ile B arasında voltaj ölçümü yapıldığında pozitif bir değer çıkıyorsa nedir? Bir iki dakika düşünün bakalım. Ve cevap verin. Charge carrier type elektronlarla mı iletiyor, hollarla mı iletiyor? Evet. Var mı? Cevaplayacak olan. Yok mu cevaplayacak olan? Yok mu arkadaşlar cevap? Deminden beri ne anlattım ben ya? No answers? Come on. How many are we? Well, we have so many people. So, you don't know it? It's a simple question. Okay. Arkadaşlar ben buradayım yazabilir misiniz hemen bir iki dakika içerisinde? Could you please write I'm here in the next 2 minutes? Okay. So at least you're there, but you don't know the answer. That's fine. Okay. I will try to explain it. Okay. So here's how it works. You use your right hand rule, okay? And you say that you assume first, if they were electrons, you have magnetic field there. If they were electrons, let's say, if they were electrons, the electrons would be flowing in this direction, right? That would be the flow direction of the electrons. So you point your index finger along the electron flow direction. Magnetic field is upwards. So and your thumb, which is showing in this scenario, this direction, would be showing the direction of the force if it was a positive charge particle. So the direction of the force for negative charge particle is this way, FBE, let's say. And if the material was conducting with electrons, then this part of the plate would be charged negatively. So the voltage drop that you would measure would be negative. Okay, for this configuration. So for voltage values larger than 0, this, the charge carriers cannot be electrons. They should be positive charge particles. They should be holes. For electrons, the voltage drop is negative. So you say that if the voltage drop is negative, it is conducting with electrons. Okay. Arkadaşlar gayet basit bir şekilde sağ kırımını uyguluyorsunuz. Mesela diyelim ki elektronlarla ilettik. Elektronlarla ilettiğimizde parmağınız, işaret parmağınız elektronların akış yönüyle aynı olacak. Orta parmağınız manyetik alanla aynı yere bakacak. Bu sefer baş parmağınız işte şu yönü gösteriyor. Şu an göstermeni gösteriyor. Ama ne yapıyorduk elektronlar için? Elektronlar için tam tersine çeviriyorduk kuvveti. O zaman diyoruz ki elektronlar için kuvvet bu yönde uygulanır. Elektronlarla eğer olsaydı, elektronlarla iletiyorsaydı elektriği. O zaman bu taraf işte eksi yüklü olacaktı. Dolayısıyla VAB eksi olur. Dolayısıyla elektronlar ilettiğinde VAB eksi olmalı diyoruz. Tam tersi durumda da hollarla ilettiğinde de VAB artı olacaktır. Dolayısıyla sorumuzun cevabı bu kadar basit. Sınavda sorarım ben bunu. Ona göre. Okay. So now we have an example here. I'm not going to get into details of the calculation, but I will show you how it's done. So we have a strip of copper 2 mm thick, 1.5 centimeter wide, and we pass a current of 75 amps. So first we find the current density. Okay. Current density is what? Current divided by area. And that is, in our scenario, here's how you're going to do it. Current is 75 amps. Area is 2 millimeters. To 10 minus 3. Multiply by 1.5 centimeters. 1.5 10 minus 2. That's your current density, and that should be about 2.5 25, sorry. Yep. 25 10 to 5 ampere per meter square. Okay. So that's the current density. That's how you do it. And the next step will be, so you know the current density. So you take this equation. You have to find so it gives you the voltage drop. Okay. So you need to get the easy as well. So how do you get the easy? Easy would be voltage divided by distance, right? Voltage is 0.81 micro means 10 minus 6 volts, and the distance is 2 millimeter thick, 1.5 centimeter long, so centimeter 1.5 10 minus 2 meters. So, and this one should be 7 should be 0.27, 0.54. Right. Yep. 0.54 10 4 volt per meter. Okay. That's the E field value. And you put everything in. So you put more Q here. Since it's electrons, it's 1.609 times 10 minus 19 coulombs. Easy is easy. Vy is given as, the magnetic field is given as 0.4 Tesla. So you just put 0.4. And current is given as, current density is given as, we found it as like this. So you can do the rest of calculation. There's a minus sign here because it's electrons, so you get positive value for number of particles per unit volume, which is the concentration of the mobile electrons in copper. So I don't know if I can do this calculation for you. Let's say it should be about 1.1 10 to 20, I guess, in that scale. Okay, and the unit should be 1 over meter cube. I'm not going to do this in Turkish because it's very straightforward. You just apply the equation. Okay, any questions about this one? Any questions about anything else? I guess there's no questions. I'm not going to do this exercise, but if you're interested in, deep physics, you can do this. This is about quartz. It's a pretty long question. It's going to take too much time, and it doesn't worth solving it. So if you have interest, you can solve it, and if you have questions about it, you can always ask me about it later. And now I would like to switch to a new subject. Okay, so week 8. We are at week 8, and this is week 8 subject. Okay, so in the previous chapter, we dealt with, forces on moving charges due to magnetic field. Now we are going to get into source of magnetic field. How you make a magnetic field? The magnetic field is generated by moving charges. We kind of mentioned that before. Okay. And how does it? How do you find the magnetic field generated by a moving charge? So we remember E field from a charge. That was 1 over 4 pi epsilon 0 q over r square, and the E field was a vector field. It was in radial direction. Magnetic field is very similar to that. We have 1 over 4 pi, instead of 1 over epsilon 0, we have mu 0. Okay, magnetic constant. And we have 1 over r square as well. So field also reduces by square of the increasing distance. Okay, and it is also proportional to the amount of charge that's moving. In E field, it was also proportional to the amount of charge. And the last part is slightly different. In the last part, in addition to the this radial vector, we have the velocity, which is not a unit vector. We just multiply everything with velocity. Okay, here's what I mean. For a moving charge, for example, here, the E field doesn't change. It's not related to movement. It's in radial direction. But as you are moving it, so what's really happening is the B field is the magnetic field is not parallel to the E field, but it's going to be a cross product of the velocity vector and the radial direction. So at every point, the magnetic field will be pointing in different directions. So let's say this is a simpler situation. You have your velocity vector here, and for example, magnetic field in this direction, in this point. Let me use a pointer here. If you're interested in calculating magnetic field in this point, you take the radial direction, point R here, and you do cross product of velocity vector and this radial vector. So in this scenario, okay, remember, from the previous week, how we were applying the right-hand rule. Okay, for example, for A cross product B, the index finger always showing the direction of the first vector. The middle finger is always showing the direction of the middle, the second vector, and the result would be the thumb. Okay. So the first vector is velocity. It is showing this direction. The second vector is the r vector. That's going to be your middle finger. Then the magnetic field will be showing in this direction. Okay, and this holds for everything here as well. If you apply that, it holds. But since this this looks like for all of the points, B field will be looking like this. You apply a simpler right-hand rule. This is a curling fingers right-hand rule. Now for this one, what you do is you take your right hand, the velocity vector, you align it with your thumb, and the curl of your fingers is showing the circular pattern of the magnetic field vectors. Okay, so your thumb should be showing the velocity vector direction, and your fingers will be showing the direction of the magnetic field vectors. Arkadaşlar özet geçeyim. Yani bu konuya zaten aşinasınız. Manyetik alanla elektrik alan birbirine benziyorlar hesap olarak. Yani 1 bölü 4 pi ikisinde de var. 1 bölü epsilon 0 yerine mu 0 var. Manyetik sabit. 1 bölü r kare yine orantılı. Yani r kare ile ters orantılı. Manyetik alanın büyüklüğü. Q ile çarpıyoruz. Yine elektrik yük miktarıyla doğru orantılı. Elektrik alanda olduğu gibi. Fakat sonda bir değişiklik var. Burada elektrik alanını radyal yön vektoriyle çarpıyor. Çünkü radyal yönde sadece bu unit vektör. Herhangi bir şeyi yok, büyüklüğü yok. Ama manyetik alanda velocity yani parçacığın hız vektörüyle şeyin cross product'ıyla çarpıyorsunuz. Radyal vektörün cross product'ıyla çarpıyorsunuz. Şimdi bu ne demek? Mesela şu sağ üstteki imaja baktığınızda İşte velocity vektör, hız vektörü şu şey yönde, bu yönde ilerliyor. Gördüğünüz yönde ilerliyor. Mesela şu noktadaki manyetik alanı bulmak istiyorsunuz. Şu kırmızı ile işaretlediğim noktadaki. Oraya doğru parçacığınızdan bir doğru istiyorsunuz, bir vektör istiyorsunuz. O sizin o nokta için radyal vektörünüz oluyor. Radyal vektör, bu cross şeyi yaptığınızda, mesela cross product yaptığınızda sağ kuralıyla, daha önce kullandığımız sağ kuralından bahsediyorum. İlk vektör velocity vektörü sizin işaret parmağınızla aynı yönde olacak. R vektörü, hatta direkt onu da getireyim buraya. Aynı yerde bekliyorum. Özür dileyerek. Okay. V vektörü işaret parmağı. R vektörü orta parmak. Okay. Evet. V vektörü işaret parmağı. R vektörü orta parmak. Manyetik alan şu da şu yön oluyor. Yani sağ ay kuralı, bildiğimiz sağ kuralı bu duruma uygulanabiliyor. Ama şunu fark edeceksiniz. Herhangi bir uzay nokta için yani bu manyetik alan hep zaten mesela şu üst taraf için hep aynı yöne bakıyor. O yüzden daha basit bir sağ kuralı uygulayabilirsiniz. Buna kıvrılan parmaklar sağ kuralı diyoruz. Şu sağ elinizi alıyorsunuz. Bu baş parmağınızla velocity vektörünü aynı yöne baktırıyorsunuz. Parmaklarınızın kıvrım yönü manyetik alanın bu dairesel vektör ile aynı yöne bakıyor. Okey. Her nokta için yine bu sağ kuralı uygulayabilirsiniz ama genel dairesel yönünü bulmak için şu kıvrılan parmaklar sağ kuralı uygulamak daha uygun. Tamam. Sorusu varsa cevaplayabilirim. Galiba. Okay. So now let's move on. So you can see the magnetic field, vectors here, and this is magnetic field vector lines. For example, when you get closer to this is by the way, this is showing the direction of the movement of the, positive charge particle, and when you apply your right-hand rule, you will see that, the magnetic field is in this direction, and this is, what magnetic constant is. Mu0 is 4 pi 10⁻7 Tesla meter per ampere, or Newton second square, or Coulomb square. And you will see that later, later in the course, I will prove you that, 1 over mu0 epsilon 0 is equal to square of speed of sound. Okay, there's an interesting relationship between mu0 and epsilon 0. 1 over mu0 epsilon 0 gives you square of speed of sound, and I will explain you how we get there when we get into the details of Maxwell's equations later. Okay. So let's do an example. We have minus 4.8 microcoulombs of charge moving at a constant speed of 6.8 times 5 meter per second in positive x direction relative to the reference frame, at the instant when the point charge is at the origin, what is the magnetic field vector it produces at the following points? I'm not going to do all of them, but some of them. So let's do it. So we will use this equation. We can use this simple form. The cross product is always can be converted to QV sine phi, as we saw before. If you are just interested in the magnitudes. So this is asking us magnitudes here. Mu 0 is known. For example, for A, the distance is 0.5 meters. So you are going to put 0.5 meters instead of R. Q is, minus 4.8. Let me copy this. We are going to be using it. Q is minus 4.8. The velocity is 6.8 and 5. Here, phi is the angle between r vector and velocity vector. Here, r vector, we are talking about x is 0.5, and the particle is moving in positive x direction. So let's say here this is positive x direction. Okay. We are interested in finding magnetic field here, and we are moving here. The angle is now then 0. When the angle is 0, when the angle is 0, what happens is sine 0 goes to 0, and the rest of the equation doesn't make sense. Everything becomes 0. So the magnetic field is going to be 0 at position x equals to 0.5. So let's do something else. Let's do C, for example. Here, R is not 0.5 because now we are talking about this kind of point. Okay. So we have X there. And if this is the axis, we are talking about here. Let's say this is 0.5 meters. This is also 0.5 meters. So the R will be 0.5 square root 2, and the angle will be 45 degrees. Right, if this is Z and this is Y. Okay. So when we go back here, so it's going to be square of 0.5 square root 2 sine 45, okay. And mu 0 is just given here. I never memorized those stuff, to be honest. For pi 10 minus 7. Okay. So you can calculate this. And what would be the direction? So B field is so what would be the B field direction? So is it a positive? It's a negative charge particle, right? Okay, so it's a negative charge particle. For a negative charge particle, you just reverse the direction that you may find here. So normally it should be towards positive y here. Then for a negative charge particle, it should be negative y. Okay, because here you get q negative, the direction will be reversed. Okay, let's say here in negative y direction. Okay, do you have any questions about this? This is pretty straightforward. I'm not going to spend too much time on this. So we can move on if you want. So we did that. Let's do this one. So there are two protons parallel to the x-axis in opposite directions at the same speed v. At the instance shown, find the electric and magnetic force on the upper proton compared their magnitudes. So each of them will apply a magnetic field. So the bottom one, for example, the force will be QVB. Okay, let's see. Let's use some pointers here. So let's talk about the magnetic field that will be generated. So velocity vector is here. R vector is pointing up. Okay, so the magnetic field will be towards you guys. Magnetic field applied by the moment of this charge will be towards you guys, towards us, right? And when we talk about the magnetic field applied due to this particle, so the velocity is that way, so it's going to be towards V again, towards us again. Okay, for this particle too. So what is the then magnetic force, direction of magnetic force felt by the upper particle? B field, so you use the previous right-hand rule. You use this right-hand rule, okay? This one here. So velocity vector is A. Magnetic field vector is B here. And the thumb shows you the direction of the force, FB. For this one as well, magnetic field is your middle finger. The velocity vector is A, so your thumb is showing downwards, and this is the FB. Oh, sorry. This is the FB. Okay. And the value FB, for FB, let's calculate that. FB is QVB. Since we are interested in magnitudes only, and since there's no angle in between, we say FQ V B, and B is this guy here. So there will be a sine phi too, as you see here. But since phi is 9 degrees, they are just right on top of each other. We take it to be 1. Okay, so we just end up having mu 0 qv over 4 pi r square. R there is a unit vector, so it doesn't affect things. Okay, and what you have is then q square, d square. Okay, this is the FP. Okay, FE is this one. So since we are on interest in, again, magnitudes, FE is 1 over 4 by epsilon 0. QA, QB are just Q's. Okay, Q, R is the same R. We can ignore the unit vector. Okay, this is FE and FP. So what is the ratio of FE and FP then? Let's find the ratio of FE and FP. So it's going to be ratio of this one to this one. So, okay. So here 4 pi's cancel out. Okay. Q squares cancel out. R squares cancel out. And what you have is then one over epsilon 0. Let's see. 1 over epsilon 0 mu 0 v square. Sorry about this. Okay. 1 over epsilon 0 mu 0 is just c square. So and you have c square over v square. Okay. Let me clean this a little bit. Okay. Okay. So you end up having the ratio of force, electric force to magnetic force is C square over V square. So since it's saying that V is small compared to the speed of light, you say that, the force of electric force is much larger than the magnetic force. And that's typically the case in the universe. Electric forces are much stronger than the magnetic forces. Typically. Arkadaşlar burada iki tane proton ters yönlerde gidiyorlar. Belli bir hızda, aynı hızlarda. İşte birbirlerine bir manyetik alan oluşturuyorlar. Bu manyetik alan dolayısıyla bir kuvvet hissediyor ikisi de. İşte bu manyetik kuvvetle elektrik kuvvetinin birbirini kıyaslamamızı istiyor bu soru. Manyetik kuvveti hesapladık. Q ve B'yi işte şeyden bulduk. Mu 0 bölü 4 pi Q kere QV bölü R kareden. İşte yerini koyunca burada FB'de QV çarpı mu 0 bölü 4 pi QV bölü R kare eşittir mu 0 bölü 4 pi Q kare V kare bölü R kare çıkıyor FB için. Fi için de 1 bölü 4 pi epsilon 0 QA QB bölü R kare bizim denklemimiz. İşte ikisi de Q kare bölü R kare oluyor o yüzden. Çarpı 1 bölü 4 pi epsilon 0. Bunlar birbirine oranlayınca 1 bölü 4 pi epsilon 0 Q kare bölü R kare bölü mu 0 bölü 4 pi Q kare V kare bölü R kare bize 1 bölü epsilon 0 mu 0 V kare veriyor. Hatırlarsanız bir önceki slaytta şurada C kare eşittir 1 bölü mu 0 epsilon 0 demiştim. C burada ışığın hızı. Dolayısıyla bizim denklemimizin sonucunda biz ne buluyoruz? C kare bölü V kare biliyoruz. Ve şu anki hızı ışık hızının çok daha altında olduğu için resmen Fi bölü Fb çok büyük bir değer çıkıyor. Yani Fb negligible oluyor. Fi'ye göre. Yani elektrik kuvvetleri manyetik kuvvetlere göre çok daha büyük oluyorlar arkadaşlar. Normal hızlarda evrende. Okay. Now let's move on. So far we dealt with, magnetic forces, magnetic fields due to, single movement of single particles, single charged particles. But now I would like to explain, what happens for a, segment of current element. Okay. So the same logic, we did previously. dq is nq_adl, the amount of charges per, for this current element. So number of charges per unit volume multiplied by charge per particle multiplied by area, cross-section area of the current element, multiplied by length, dl, the differential length. So dB is, just mu 0 or 4 pi dq dv sine phi over r square. And if you reorganize things, dq is nq_adl, nq_vda is the current. We know that it's the definition of it. And then dB is mu 0 4 pi idl sine phi over r square. Then dB is or dB, in general form, dB is in vectorial form mu 0 over 4 pi I dl cross product r over r square. You will still see that we are assigning a vector value for length, which is not, very intuitive, but it's what it is. Then B field is in general form, if you want to, consider longer lengths, mu 0 over 4 pi integration of I dl cross product r over r square. Here, the dl's that we typically consider, we just enter the number of the length. The integration is that simple typically. Arkadaşlar burada tek bir parçacık yerine bir akım geçen bir telin şeyi nasıl bulunur? Uyguladığı manyetik alan nasıl bulunur? Onu bulmaya çalışacağız. Onunla ilgili matematiksel denklemler bunlar. İşte daha önce yaptığımız gibi bir akım elementinin üstündeki anlık yük miktarını buluyoruz. Ona diyoruz ki dq işte nq_adl. Burada n hacim başına düşen parçacık sayısı. Q her bir parçacığın yük miktarı. Mesela bir elektron için -1.609 10 üzeri -19 kulomb kadar. A'da işte bu telin kesit alanı, length DL'de burada diferansiyel uzunluk, yani en küçük olabilecek tel uzunluğu. Şimdi yerine koyduğumuzda manyetik alan denkleminde dB eşittir mu 0 bölü 4 pi dq vd sin phi over r kare üzeri r kare çıkıyor. dq yerine nq adl koyduğumuzda, tekrar organize ettiğimizde nq vd ve drift velocity burada bizi ilgilendiren a zaten akımın kendisine eşit. Dolayısıyla dB uygulanan manyetik alan bu küçük tel için mu 0 bölü 4 pi 0, mu 0 4 pi, mu 0 bölü 4 pi akım çarpı dl diferansiyel uzunluk sin phi, işte sizin ilgilendiğiniz noktadaki nokta için oraya uzanan r vektörüyle hız vektörü arasındaki açı sin phi bölü r kare, ilgilendiğiniz noktanın sizin elementine, current elementiyle olan uzaklığı. Daha genel formu işte cross product şeklinde yazabilirsiniz. Mu 0 bölü 4 pi I dl vektörü cross product r vektörü bölü r kare. Buradaki gördüğünüz gibi yine uzunluğa bir vektör atadık. Çok intuitif değil ama böyle arkadaşlar. Farklı kolaylıklar olduğu için bu şekilde ele alınıyor. Normalde akımın bir yönü var, uzunluğun bir yönü yok. Genel formülde de işte bu dl'i entegre ederseniz toplam manyetik alanı buluyorsunuz. Şimdi gelelim bir problem çözümüne. Okay, now, so let me do it this way. So we have a copper wire that carries a steady current of 125 amps. Find the magnetic field due to the 1 centimeter segment of this wire at a point 1.2 meter away from it. If the point is at A, P1 at outside the segment, and P2 here, and it is 30 degrees angle between, the wire. So I will do P2, you can do P1, okay? So here, this equation, when you do integration, dl will be just, L itself. For example, you will integrate from 0 to 1 centimeter. So it's going to be the length itself. It's going to be just same as multiplying by 1 centimeter. So you just replace it with just L. Easy, okay. And you find the total magnetic field if you just do that. So here mu 0 is 4 pi times 7 10 minus 7 Tesla or meter, right? That was the units. Tesla meter per ampere, sorry. Okay. Tesla per ampere. Units. You have 4 pi there. The current is 125 amps. The length is 1 centimeters. 1 times 10 to the minus 2. Sin phi for P2 is sin 30 degrees. Sin 30 is what? Sin 30 is 1 over 2, right? So 0.5. R is a distance, that's 1.2 meters, it's given here. Okay, so and square root of that. Now we can calculate this. For this is, by the way, current. This is meters. This is meter square. Meter square. Okay. Meter square and these 2 meters cancel out each other. Okay. And and amperes cancel out each other. So you end up having Tesla as expected. So 4 pi's also cancel out each other. So what you have is, now let's calculate that. 125 multiplied by 0.5 divided by 1.2 divided by 1.2. It's about 43.4. Point 4, 10 minus 9 Tesla. Okay, that's how you do it. Sorry about the mess, but while watching the recording, you will find that this is quite good explanation of the problem. Okay, any questions about this? I'm not going to do it in Turkish because it's very straightforward. We just apply the equation. Okay, are we good? Okay, I think we are good. So let's do this one. So we have now two parallel wires that are 5 centimeters apart, carry currents in the opposite directions, find the magnitude and direction of the magnetic field at point P. So again, the equation just simplifies to B mu 0 IL sine phi. So here we have 12 amps of current in the upper one. Let's find the magnetic field due to the upper wire first. Let's grab this. It's mu 0. The length is, let's grab something for length 2. Length is 1.5 millimeters. 1.5. 10 minus 3. And the sine phi is, the angle here. The velocity is towards right, and the angle should be this angle. Let's find that out. So this is 8 centimeters. This is in total 5 centimeters, right? So this is 2.5 centimeters here. So sine phi, this is phi, should be 2.5 over 8. And we just write that down. A multiply R is 8 centimeters. That's 8. 10 minus 2. Okay. So the current is 12 amps for the upper one. Let me check if I can do this quickly. I think I can do this quickly. Let me try to simplify it first. So instead of 8 times 10 to the minus 12, let's make it 8 multiplied by 8 and take this out. We have another 8 here. Yep. And this 8 will also go down. Now you have 2.5 there. Okay. 4 pi's cancel out. We have 10 minus 7 here. 10 minus 10, 10 minus 6, 10. Okay. So let's calculate this. 12, 1.5, 2.5, divide 8, 8, 8. Okay, 0. What was it? 0.088. Yeah, 0.088. Let's call it. It 10 minus 6 Tesla. Okay, that is for the upper one. For the bottom one, and you should also say that for the upper one, the magnetic field direction will be, so when you use your right hand rule, it's going to be towards the paper. For the bottom one, it will be towards the paper, towards the screen plane as well, when you apply your right hand rule. So they need to be added together. So everything is the same. This was 12, then this is 20. Then the total field will be actually, if this is 1, this is 2, 3 multiplied by this. Okay, so B total, let me call it then. B total will be 3 multiplied by this, which is basically going to be 0.2 in a second. 10 minus 6 Tesla. I hope I didn't make any calculation mistakes, but that's how you solve it. Okay, I'm not going to explain this in Turkish as well, because this is also very straightforward. We are just applying the formula. Sadece burada arkadaşlar yönlere dikkat edeceksiniz. Sinüsü nasıl hesapladığımızı iyi bakın. 2,5'u 8'e bölüp direkt koydum oraya. Yönlere de iyi bakın. İkisinin toplamı alınıyor burada. İşlem hatası yapmayın sınavda. Okay, we have about 8 minutes and I think I can do lots of things in those 8 minutes. I will cover slide 9 and the rest of the slides. Ooh, we have lots of slides. Rest of the slides, maybe I can do 10 and 11 too. Maybe I should do that too. Okay, so we did that. Those two were simple, but this is not that simple. So what we have here, we have longer segments, and we are interested in calculating contributions of an entire segment on just point P. So here, this for this region, for this segment here, for example, the R is just X. The R value is smaller than this segment, which is just square root of x squared plus y squared, and the angle is also different. So we need to integrate from minus a to a for this formula, but we need to be very careful about that. So the current is known, constant. It can go outside of the integration. By the way, there's a typo here. This integration is going to be not minus b, not db. So I goes out, 4 pi out goes out. So for the angle here, okay, is sine of that angle is what? Sine, let's go, well, crap. This is phi, okay, sine phi over there is equal to sine pi minus phi, right? So it doesn't really matter if you use sine or sine minus pi minus phi. And then sine phi is equal to this length divided by this length, which is x over square root of x squared plus y squared. Okay. And the r value is this one. And square of that is, r squared is x squared plus y squared. So 1 over r squared multiplied by sine phi gives you x divided by square root x squared plus y squared to the power of 3 over 2. Okay. And if you do that integration, if you try to do that integration, you will find that it's not that easy. So you use table of integrals. You just search online for table of integrals and you look for something similar. I found something similar online. Okay. Okay. So here the variable here is y, arkadaşlar. Okay, that's important. The variable is y. dy is the variable. So x is like a constant here. So it doesn't really, so here it's confusing. That's why I kind of want to point. So you replace this by y. Okay. Okay. Okay. Here a is the x. Okay. Near a is the x. Y, x is the y. Okay. So think about that way. And okay, and we have an extra a here, which doesn't really change things because it's just a constant. Okay, so and let me replace this with x. Okay, this is x. I don't want you to get confused because of name of the assignment of the variables. Okay, and this is x. We have extra x here. Okay, so the integration is just, x over x squared. So these x's cancel out. We just will have x left here. We have, so maybe I should do it more explicitly. Let me do it more explicitly. Take time, but it worth it. I don't want you to get confused. So if you do this integration, and I need to grab something from the previous week. Oh yeah. Let me grab this one. So let's focus on here. So we are going to integrate from minus a to 8, minus a to a, sorry. And inside will be pretty much like this. It's going to be 1 over x, yes. That's basically the integration here. Let me put these aside first. So this is before this one, you have this one, okay? And we get this using this table of integration, okay? From here, we get here. Since we have an extra x here, we have x, y, sorry. Very sorry. So y square, okay? We have from here, we get here, okay? We have xy over x squared, square root of this is x2. Okay, square root of x squared plus y squared. And you put a and minus a instead of y here and subtract from each other. So it's going to be a over x multiplied by square root of x squared plus a squared minus a over a minus a square root of minus a squared plus x squared. Right, this is x, not a. X. So in total, at the end, after you do this calculation, you get for B field mu 0 I over 4 pi 2a divided by x square root of x squared plus a squared. So that's the exact calculation. So if you get p very close to 0 to origin, if you make x 0, this goes down to 2a over a, it's just 2 over x, so it's going to be mu 0 I over 2 pi x for, if you get, point P to origin. Okey, arkadaşlar bunu Türkçe'de açıklayayım. Biraz da karıştı, o yüzden Türkçesi de açıklamak iyi olur. Vakit geçiyor ama olsun. Şimdi daha önce bir ufak bir segmentin işte bir noktalık şeyine baktık. Manyetik alana baktık. Bu sefer segment büyük ve bütün segmentin şeyine bakmak istiyoruz. Katkısını bulmak istiyoruz. Toplam katkısını bulmak istiyoruz manyetik alanda. Şimdi bunu ufak ufak segmentlere ayırıp işte hesap yapmamız lazım, toplamamız lazım. Ama her bir segment için hem phi açı değeri değişik phi hem de uzaklık değişik, r değeri değişik. Mesela burada x iken burada kök içinde x kare artı y kare. Şimdi dolayısıyla denklemimizi yazıyoruz. Mu 0 I bölü 4 pi işte eksi a'dan a'ya integral alınacak. X dy bölü x kare artı y karenin 3 bölü 2. kuvveti. O nereden geldi? Sin phi x bölü x kare artı y karenin kökü x bölü kök içinde x artı y kare r kare değeri de x kare artı y kare. İşte y sıfırken direkt x'e düşüyor r. Sinüs değeri de direkt 1 oluyor. Neyse. X'i çarptığınızda işte x bölü kök içinde x kare artı y karenin pardon çok üzüldüm. X bölü x kare artı y karenin 3 bölü 2. kuvvet oluyor. Dy de var. Şimdi bunun integral o kadar basit değil arkadaşlar. Y burada değişken. O yüzden integrale bakıyorsunuz. İnternetten integral tablolarına. Orada şey göreceksiniz. Benzer integrali göreceksiniz. Burada mesela ben şey bulmuşum. Direkt aynısını bulamamışım. Ama mesela dy bölü x kare artı y karenin 3 bölü 2. kuvvetinin şeyini bulmuşum. İntegralini bulmuşum. Orada işte tepesine bir de x ekliyorum. Bu fark etmiyor. Çünkü x burada değişken değil. Dolayısıyla x, y bölü x kare artı x kare çarpı kök içinde x kare artı y kare şeklindeki integral sonucu kullanabiliyorum. Yani şunu kullanabiliyorum. Onu kullandığımda a'yı koyuyorum. Eksi a'yı koyuyorum. Birbirinden çıkarıyorum. O zaman sonuç mu üzeri bölü a. Mu üzeri i bölü 4pi çarpı 2a bölü kök içinde x çarpı x kare artı a karenin kökü oluyor. Bu bizim exact solution'umuz. Yani net çözümümüz. Şimdi P noktası x kadar uzaktayken bu çözüm geçerli. Peki x'i sıfıra getirirsek yani P noktasını orijine getirirsek o zaman manyetik alan ne olur diye baktığımızda manyetik alan mu üzeri I bölü 2pi x oluyor. Okey. Pardon. Çok yanlış. Ben ne yaptım ya? X'i sıfıra getirirken kastım şu arkadaşlar. A'yı çok büyük yaparsam, sonsuz uzunluk yaparsam teli. Çok özür diliyorum. If I make, a much longer than x, I'm not taking x to 0. Because if you take x to 0, the magnetic field will be 0. If I'm just making a much larger than x, and when that happens, you take limit at the infinity for a, and if you let this goes to 0, it's going to be a multiplied by x, a is cancelled out, and you get mu 0 I over 2 pi x. Arkadaşlar i'yi sonsuza alıp limitini alıyorsunuz. Bu sefer mu 0 I bölü 2 pi x çıkıyor. X'i 0 yapmıyorsunuz. X'i 0 yaparsanız çünkü telin üstünde manyetik alan 0 olacaktır arkadaşlar. Orada hata yaptım. Kusura bakmayın. A çok daha büyük olduğunda x'ten. Bu denklem geçerli. Bu da sonsuz uzunluktaki teller oluyor. Burada mesela onunla ilgili problem çözeceğiz gelecek hafta. İşte sonsuz uzunluktaki teller var. İşte şu noktalardaki manyetik alanı bulacağız. Yine benzer şekilde sonsuz uzunluktaki tellerin ortasındaki manyetik alanı bulacağız vesaire vesaire. Onu şimdi yapmıyorum çünkü vakit bayağı geçti. Siz de yoruldunuz bayağı. Her şey için teşekkür ederim arkadaşlar. Ders dinlediğiniz için teşekkürler. Yalnız biraz daha ilgi bekliyorum derste. Soru soruyorum, hiç cevap vermiyorsunuz. Yani sınavınız iyi geçti diye salmayın. İkinci sınavlarda farklı stratejiler uygulanabilir. O yüzden tavsiye etmiyorum salmanızı. İyi günler diliyorum. Her zaman gibi önümüzdeki bir saat boyunca sorularınızı sorarsanız ben cevaplamaya çalışırım. Görüşmek üzere arkadaşlar.